Okay, so we are doing infinite horizon MDPs now. And just a very quick recap. Uh, so, what's the problem when we talk about infinite horizon? What's the mathematical problem? Reward can diverge, right? So if we look at this policy, right? Uh, if I just said, what's the total infinite horizon value reward for this state? What's it going to be? Infinity, whatever that means. And how about this state here? Infinity, right? Because eventually you're going to get to S1 and that has infinite value. And so we have to somehow deal with that, right? Because if you have one policy that collects a reward of 1 every time step and another that collects a reward of 2 every time step, you'd like to be able to tell the difference between them. Not just say, hey, they both have infinite value. Okay? So the standard, and there are several ways to deal with this. The way we're going to deal with it is discounting, and this is pretty common and maybe the most easy to handle. I'll just give you a little insight into one other way that is used to deal with this. So what other people will do is, and this is much more rare, but people do it. It's called average reward, and what they'll do is they'll write down this expression, 1 over t, where t is the length of time, and then they'll have, this is going to be an expectation, we'll have an expectation over a summation of t, equals 1 to big T. Little t equals 1 to big T of r of t, right? Like this. So this is what they'll deal with, and the thing that they'll try to optimize is this, right? So you take this average, this is the average reward per time step, and then you say, what is that going to be in the infinite limit? And it's messier to deal with. That's all I'm going to say, and we're not going to deal with it in this class. So the trick we're going to use is adding discounting. So beta is a discount factor. There's lots of symbols that are used for discount factors. Gamma is another common one, but beta is pretty common. And it's going to be something less than 1, usually greater than 0. And you can see because of that, beta, we're going to have an influence that dies off as time goes on, right? So rewards that are further in the future are not going to be as important to us when we're thinking about what to do, right? And that's just one way of dealing with this problem. So we define this, and the main point here was that if we do define the value function in this way, right? So make sure everybody understands this expression. Any questions about this? So if we say what is the maximum value that a policy could have, it turns out to be this thing here. If you do just a little bit of algebra and infinite series, where R max is the maximum reward you could get anywhere in the MDP, okay? The one-step reward. And this is kind of interesting because qualitatively it makes sense. If beta is small, right, the max reward is going to be what? The max value is going to be what? It's going to approach what?
Could you please explain why did you consider all the reward values to be the same on max?
Oh, so we're just trying to get an upper bound, and so here here the reward is a random variable. We don't know what it's going to be. So to get an upper bound, we just say, well, we're going to bound all the rewards. It's a very loose upper bound, right? We're going to bound all the rewards by a constant, which is the maximum the reward could be. And so because we bound it by a constant, we're able to factor it out of this summation and the expectation and sort of get a nice expression. So it's just a very loose, coarse upper bound.
But wouldn't that affect the policy because we are taking
right. So we're never actually going to do this in our solutions. The point here is that we want to say that because we're using discounting, we've solved the problem of having infinite values. And we've solved that, and we can see that here because the maximum value any state could have for any policy is this. This is just showing that there's not going to be any infinite values under this definition of the value function, right? But we don't use this in a solution concept ever. All right. Now there's a nice interpretation of this term here. Well, first, if beta is very, very small, like let's say it's close to 0 or 0, right? It can be 0. What's the maximum value any state could have? Just R max, right? So if the discount factor is 0, that means all you care about is the immediate reward. Does that make sense? Right? If we go back to our definition, the only thing, if the discount factor is 0, the only time that it's going to actually register something other than 0 is when t is 0. Because 0 to the 0 is 1 for some reason, for convenience here. Now, there's a nice interpretation of this term here. And let's just look at the case when beta is very close to 1, right? When it gets closer and closer to 1, you care more and more about the future. And you can see this thing starts to get really large, this term here, right? Which makes sense. Now, this term, 1 over 1 minus beta, is sometimes called the effective horizon size. That's a very common term for it. And the reason, you can sort of see why from this expression. So if we said we're in a finite horizon setting, right? Finite horizon, you had a horizon of h, and you get a max reward every time step, what's the value going to be? H times R max, right? So here we see the max we could get is R max times 1 over 1 minus beta. And so beta, 1 over 1 minus beta, is kind of playing the role of this effective horizon. And so when people say they're doing infinite horizon MDPs, really there is some horizon upon which the optimization doesn't matter, right? And sometimes we sort of treat that as, that horizon is 1 over 1 minus beta. And you can see it has the behavior you'd like. When beta is 0, the effective horizon is 1. When beta is close to 1, the effective horizon gets really large. Okay? So that's just a term you might see sometimes. And I talked about the motivations in the video, right? The probability of death motivation is pretty interesting. You can actually sit down and derive that with a little bit of algebra. All right, and I'm not going to go over this too much because I want to make some more progress, but basically every MDP has a optimal policy under this value function, which means there is a policy that can achieve a value as good as any other policy across all states. Right, that's what we mean by an optimal policy. And can there be more than one optimal policy? Yes. And why is that?
Because there can be multiple paths that have equal values, so you have two actions that both have a guaranteed output of 1.
Right. So you can achieve the same thing in multiple ways, roughly speaking, and that same thing could be the optimal thing. So and sometimes there can just be completely different things that get the same value, and those policies that do those different things would also both be optimal. All right, so now the computational problems. We define this new form of value function, infinite horizon. It's a mouthful. If you really want to get it right, it's expected, infinite, cumulative, infinite, discounted reward, right? That includes everything. And we want to study policy evaluation and policy optimization, these two problems. These are the key problems. You'll see these problems in reinforcement learning as well. That people will talk about wanting to evaluate policies and wanting to optimize policies. And so let's first start with policy evaluation. How can we do this? Well, the first thing to note, and I'm not going to derive this, but if you start with this equation here, this is actually easy to derive. If you start with this equation and you factor out the first term, like the first reward that you get, and then you have the rest of the stuff just off to the side, the rest of the stuff is still going to be an infinite sum, right? And so it looks like there's going to be a recursive form. And if you do some mathematical wanking, you'll get this form here. So this is a very typical form. You've seen it in the finite horizon case, essentially. So the value of a policy at state S is equal to the immediate reward you get, right? And notice here where we've got the policy inside, right? That's the action you're going to take, plus the discounted expected value of the next state, right? Under this policy. And so we have to do a discount factor because it's one step in the future, right? That value we get in the next state is going to be discounted. So that's where this discount factor comes from. And then this is just sort of the expectation over the next states of the value of that next state, right? So it's kind of a recursive equation, right? So that's a very intuitive form of the value function. And yeah, you can derive this if you want. It's not hard to do. So just this is kind of an aside. It's kind of a mess to look at. But since the book defines things slightly differently, I think it's important to show that we're kind of still in the same game as the book. And so if you remember, your book defines sort of the MDP transition and reward function all in one package, right? So if you're in state S, you take action A, there's some probability you're going to get S prime as the next state and a reward R as the next reward. And the book, it's kind of a weird thing in the book, but you have to kind of have discrete rewards for this to work out nicely, to work with summations, or you're going to have to treat this as a density, but we won't worry about that. They're not too mathematically precise. So what I claimed earlier was that if this is how we define things, RSA and TSAS prime. I claim that we could define our functions in terms of theirs in this way, right? So the reward is just the expected reward for a state action pair, and the transition function is just you get rid of the reward from their function. Now, this is how your book defines the value of a policy. Okay? So it says you sum over all the next states, sum over all the rewards, so they've got to be discrete, and then you look at the probability of each next state and reward for the policy, right? The policy's action. And then this is the contribution for that next state and reward, right? It's the reward plus the discounted value of that next state, right? So this is how your book does it. And if you just break this down a little bit, you separate out the R and this part here, you get this, and you'll get exactly the form that I wrote, right? So it's because the algorithms are always dealing with expectations and things decompose nicely. The book, this more general form where R and S prime could be very highly correlated, we can still break them up in this way, right? So you can look at that on your own, but basically that's just an aside to try to make us in the same ballpark as the book. All right, so here's our equation. Now what we want to do is, so I'm going to give you a policy now, and I'm going to give you a discount factor, and I'm going to give you the MDP, so all the MDP stuff. And I want you to give me the value function back for that policy. And in this case, well, how big is the value function going to be in this case? Like if you think of it as a vector or a matrix, how big is the value function going to be? Size n, right? Because previously in the non-stationary case, it was size n times the horizon, right? Because we had a different value function for every horizon. Now we just have one value function. So we're just going to return a vector of size n. So we're going to be given RT, pi, and beta, and I want you to compute this. And I'm going to let you assume this equation is correct. And so what's special about this equation? If we think of v as the so each of these is a variable. Each v pi s for every possible s, that's a variable. All right?
You can update all of them at the same time.
So is there anything special about this equation in terms of v if we assume this is a constant and beta and this is a constant? Because what kind of equations are the nicest? Yes. It's linear, right? So look at this. So this is a variable, right? And it's going to be every value of s. This is going to be one variable, and this is a variable. If this is a constant, this is a constant, and this is a constant, this is a linear equation. And it looks kind of tricky because we're trying to solve for v, and it's on both sides of the equation, but we know how to deal with that with algebra, right? You just subtract it, move everything to one side. So this is a linear system. So how many variables are there? There's n variables, right? One for every state, v pi s1, v pi s2. And how many equations are there? N, right? So we can write this equation down for every state. So we'll have one equation where s happens to be s1. And on this side, you're going to have all the variables because we're summing over all the states. But there's n variables here and n constraints and n linear equations. And what do we know about that type of system? We know how to solve that, right? So n variables and n equations, we can solve that as long as all the equations are independent, which they will be here. So we can just use matrix algebra, right, to solve this, or whatever your favorite linear system solver is. And I'm going to actually show you the way that it looks if you formulate it as matrix algebra, because it's actually a very useful way to just program these sometimes. There are certain things, probably for your homework in the next week, we probably won't want to do it this way because sometimes it's nice to take advantage of sparsity, but we'll talk about that when it's relevant. But it is useful to have this view of matrix algebra because you can, a lot of times if you represent all of these things as vectors and matrices, you can write very clean mathematical expressions and you can solve things with a line of MATLAB or NumPy, right, if you want to do that. Okay, so let's look at that. So we have our states here, our n states. We have, I'm just defining the variables. So this is going to be a column vector. We're thinking of v pi as a column vector where the elements give you the value of every state under that policy. Okay, so all the bold things here are vectors. R, that's a column vector. And it's a vector, so R is normally a function of S and A in our setting. But it's a column vector here because we only care about the value of R under the policy's action. Okay? So this is a column vector of length n. And T is going to be a matrix where Tij is the probability of transitioning from state I to state J under the action of the policy. All right? So that's an n by n matrix. And if you look at these definitions and you go back to the equation I had on the previous slide, this is a nice way of writing down the value function of a policy in vector notation. Okay? So you may, when you go home, just verify that this makes sense, right? That this, especially, you really just need to verify that this product makes sense in terms of giving you the expected future value. And okay, so we know how to solve this thing for v pi, right? You just do a little algebra, and there you go. So it kind of reduces to a matrix inverse. And you can show that this is a well-conditioned matrix. It's I minus, you see this thing come up all the time. It's going to be well-conditioned for any valid transition function and any beta greater than or equal to 0. All right? So that's just a useful thing to see because a lot of times you will, when you're doing analysis, you'll use matrix and vector notation for all these quantities. Even if they're too big to actually fit in your computer, it's a useful analysis tool. All right, so any questions about policy evaluation? That's pretty simple, huh? Right. So I shouldn't ask you for questions and say it's simple, but it is relatively simple.
Just to be clear, in this context, the beta is still just a constant factor.
Yeah. So beta is always going to be a constant, and that's kind of a parameter to the problem solver. Some people include beta in the definition of the MDP, but I don't like that. I think beta is really part of the objective function that you're specifying, right? It's the discounted future reward. And the MDP definition is just how does the world work and what are the rewards. The objective function is something else, and beta is the parameter of that. And so sometimes when you're doing this, you'll play with beta. People even do this in reinforcement learning. There is just one of many other hyperparameters that have an influence that people don't really understand, but people will play with that anyway. Usually you set it small if you're having trouble. Okay, so now we're going to do policy optimization. So here we want to compute the optimal policies, and this is really what we're interested in at the end of the day. And last time we said that, okay, so we know how to evaluate policies, but there are too many of them to enumerate. Right? So how many policies do we have now? If we think about the infinite horizon setting, how many policies are there? M by n. Yeah, so we have the number of actions to some power. So what are our choices? Like every state, we have to choose an action, right? Let's say there are two actions, right? Just think of it as an n bit, as a n bit vector, and that would be 2 to the n, right? So if we have 3 actions, it's going to be 3 to the n, and so the number of actions raised to the number of states. So too many to enumerate in most cases. So we need to be smarter. And I am going to show you another way to evaluate policies later on, but this we'll just keep that. We'll use the inverse right now. So basically, we're going to talk about finding the optimal value function, right? So at the end of the day, we want the optimal policy, but our first algorithm is only going to give us the optimal value function, right? And we first have to ask ourselves, if I just give you the optimal value function, if that's the only thing I give you, can you determine what to do in a state? I say, hey, you're in a state, and I tell you, hey, this state is worth 5. Does that tell you what to do? It tells you how good it is under an optimal policy, but I haven't given you the optimal policy. So we have to ask ourselves, how do we actually, if we've got an algorithm that's just giving us the optimal value function, how do we actually compute the optimal policy from that? So any ideas?
We can use the quickly, and we can check every action, and let's say if each action gives you a maximum reward.
So he's saying we should maybe check every action, and
check the value function of next day, and check the one that gives you maximum value.
Right. So we could say, okay, what if so you're giving me the optimal value function, which means I get it for all states. And so I'm in a state, and I say, okay, what if I took action A? I could end up in any of these states here, and I can compute the expected optimal value that I would get in the next state, right? We would multiply that by beta and add on the reward. And I could do that for every action, and we would just choose the greedy action. And so this is what you would do. We're going to define the greedy policy with respect to a value function. And for lack of a standard notation, we're just going to say GR for greedy, and it's parameterized by a value function, which we're going to here have the optimal one. So this is an operator that at each state returns exactly what he was describing, the action that achieves the maximum sort of future value, assuming that you get V star in the future. All right? So if I give you a value function now, we have a definition of the greedy policy with respect to that value function. It's greedy because it's just looking at the next state and saying, hey, I'm going to get that value. And it turns out that if this is the optimal value function, this is going to be a optimal policy. All right? So similar to what we saw with finite horizon value iteration. That's how you extracted the policy as well. All right, so now let's talk about how do we get the optimal value function. And I'm not going to derive this. Bellman did this way back in the 50s. And what we can say is that the optimal value function satisfies what's called the Bellman equation. And it's actually a fairly intuitive equation. So the Bellman equation says that the optimal value at state S, right, is equal to, well, I've got to consider all options and all options A in state S and then choose the best, right? So I've got to do the max. It's equal to, and what's that max over? An immediate reward plus the discounted expected future reward, assuming that in the future you get the optimal value. Right? This is what we just described in terms of the greedy policy. We just had an argmax instead of a max. But this equation is true for the optimal value function, right? So what we know is that if we can solve this equation for the optimal value function for all these states, we found an optimal value function, okay? So our problem that we're going to try to solve is how do you solve this equation? And can we use a matrix inverse again? Yes, why not? Yeah, so this is going to put a wrinkle in our linear algebra here, right? Having a max there. So it's a nonlinear equation. It's kind of a piecewise equation with respect to A. So we're not going to be able to use a simple matrix inverse. So we're going to have to do something else. And the something else is going to be called value iteration. So we're going to end up with we'll end up with an iterative process that's going to iteratively change a value function until it satisfies this equation. And we're going to look at that now. Okay, so I think this is just what we said. So what are we going to do? One idea would be, so you've already learned finite horizon value iteration. And that was fairly intuitive, I think, right? You start, when there's 0 steps to go, I've got 0 reward, 0 value, and then 1 step to go. It's really easy to figure out, what to do there. And if I have k steps to go, I can easily figure that out with respect to the optimal k minus 1 step to go value function. So what we're going to do is we're going to say, well, let's just do that and effectively just do it a really long time. So we're not going to put a bound on the horizon. We're just going to keep on doing finite horizon value iteration for a really long time, for a really long horizon. And we're going to have to throw the discount factor in there somehow so we don't blow up. And then after we run out of time or we just get sick of running it, we're going to take that final vector as an estimate of our optimal value function. Okay? So effectively, just think of it as we're going to run finite horizon value iteration for a long time, and we're going to talk at the end about how do we determine when to stop. So there are ways of determining when to stop so that you can guarantee you're optimal or close to optimal. Your greedy policy would be optimal or close to optimal. And we'll just run it for a long time and take that value at the end. And that's a pretty intuitive thing to do, and it actually works. And we're going to prove why that works. So this, again, I'm going to revisit this because we're going to throw the discount factor in it. But this, as I said, is one of the maybe the most important operator in MDP theory. The Bellman backup, really intuitive as well. So, again, what the Bellman backup does is it says, well, assuming that you're going to get some value in the future, what's the best thing to do now in each state? And how good would it be to do those things? And so, again, the Bellman backup, basically, let's say that this is the value function you're putting into it. If you want to compute the next result for this state, you're going to say, well, how good is action A1, right? You compute the expected value of these. and then how good is action A2, compute the expected value of these, then you take the max. Right? So we've seen this equation now. It seems like we're seeing the same thing over and over, right? And it's not a coincidence. So it's a really simple operator, but it turns out that this is going to work well. And notice we put the discount factor in here. When we did the finite horizon case, we did not have this discount factor because we knew we were only going to do this a finite number of times and you're not going to blow up. Now, if we kept on running this long enough, you'll run out of precision because these iterative sums could just get too large. All right? Okay, so that's the Bellman backup. And to cut to the chase, we're just going to do this over and over and over and over. And just to give you a little foreshadowing, effectively, you can solve for the optimal value function by just doing Bellman backups in random order on any random sequence of states. And as long as you cover all the states infinitely often in theory, you're going to converge to the optimal value function. And so this is sort of the idea that we're going to try to hit for our next homework, which our TAs are designing now. We want to see basically how many Bellman backups can you do per unit time using distributed computation. And it's not as straightforward as you'd think. It would be great if you just had this shared memory, like a pure shared memory infrastructure, and you could just program Bellman backups. But you actually have to organize it in the right way in the Ray framework, which I think is going to be just as easy as any other parallel programming framework. So that's actually going to be your competition, the competition part of your assignment. How many Bellman backups can you do effectively per unit time? And you'll be solving MDPs, and we'll hopefully see that you can solve them really fast. So I'm interested in this because I'm going to take the best one and start using it probably, or we'll modify it, and that's one thing that I want to do. So this is a great way to sort of get all the ideas out there. I'll have some sort of prize too. I don't know what. All right, so value iteration. So we're going to start out initializing all the values. So now this superscript, you want to think of this not necessarily as a time to live now. It's just like the iteration of the algorithm, okay? But you can interpret it as time to live if you want, but it's not really valid. So we're going to initialize everything to 0. Turns out you can initialize to anything and this will still work. We'll see why. But, just initialize it to 0. That probably will be better than if you initialize it to a bad value that's far away from the value function. And then every iteration, we're just going to do a Bellman backup at all states, right? So this is really overall states do this. Really simple. And for the finite horizon case, we stored all of the value functions, right? At every k. Do we have to do that here? Remember at the end, we're just going to run this for a whole bunch of iterations, and we're going to return that final one. So what do we have to store as the algorithm continues?
Just the last one.
Yeah, the last one, right, k minus 1, and then what we're computing now, and that will be fine. And we're going to see later on that you don't even need to store that. You can do asynchronous value iteration, as I just alluded to. Then you only need to store one vector, and you just update them all in place. But we're going to do the traditional iterative version now because that's slightly easier to analyze. So this is value iteration, right? Pretty basic. And the question is, will this converge, right? So what we want this to do is as k gets large, we'd like this to converge to the optimal value function, right, for every state. And it turns out that that is the case. The limit as k goes to infinity of vk, and now we're thinking again of these vk as a vector and v star as a vector. These do converge, all right? And we're actually that's one thing that I do want to prove to you guys, because that is actually one of the more important properties that there is. lot of reinforcement learning algorithms, the value-based ones, are essentially based on this property. They're just stochastic approximations of this. And we'll talk about that when it's time. All right. So after we show it's converged, we'll prove that it converges. Well, we know we're not going to be able to run it forever, right? So we're then going to talk about, well, how do we know when to stop, right? So if I say your boss tells you, hey, I want you to give me a policy that's within epsilon of optimal, we're going to tell you how to run value iteration long enough so that you guarantee that, all right? So that's sort of the second thing that we'll be doing. So the first thing we're going to do is talk about convergence. And for this, it's very convenient to think in vector form again, and to think of the Bellman backup operator as an operator on vectors. So the Bellman backup operator takes a vector of values and returns a vector of values. Okay? And this is how I like to write operators. So B is the Bellman backup operator, and V is the value function that you're inputting to that operator. And then BV of S is sort of the output value for that particular state. All right? And so this is nothing but the Bellman backup again. And we can now write value iteration in a very concise way. Right? If you have this operator defined, it's just V0 is the 0 vector, and Vk is the vector you get by applying the operator to Vk minus 1. All right? So this is just rewriting everything so that we can now just manipulate easier expressions. All right. So there's a couple of, basically value iteration now turns into analyzing why this operator, if you keep applying it, right, iteratively, you're just applying it over and over and over, why does it converge to the optimal value function? And there's a few properties that are responsible for that. The first one is sort of a pretty basic property that you'd want. So we're saying we're going to apply this operator until it converges to the optimal value function, or that's what we want it to do. And it seems like if you apply this operator to the optimal value function, what should it return? The optimal value function, right? So we call that a fixed point of an operator. If you apply an operator to something and it returns that same thing, that's the fixed point of the operator. And it turns out almost just, you don't do any derivation or anything. It's just by the definitions, the Bellman backup operator does have a fixed point of the optimal value function. And you can see this by, let's plug the optimal value function into the Bellman backup. And if you looked at the definition on the previous page, you get this. And this thing here is equal to the optimal value function. That's what we saw previously. So the first property that's important is the optimal value function is a fixed point of the Bellman backup operator. Okay? And that's often when you're defining operators, that's usually how you guess at what the operator should be in the first place. So I need it to be a fixed point, and that's what they did here. And the guess turned out to be good. So the next thing the next property that's crucial is something called the contraction property. And this is all covered under a very general theory of operators. We're going to talk about it more specifically in this context. But to define the contraction operator, we need to have some notion of sort of a distance or vector length. And in MDP theory, often we use something called the max norm as the measure of distance. And what that's going to be is it's actually a very, 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 very fine, detailed notion of distance. It's just going to return the maximum element of the maximum absolute value of an element in a vector. Right? So if you apply the max norm, often they would write a little infinity symbol here, to this vector, 0.1, negative 100, 5, 6, the max norm returns 100 because 100 is the largest absolute value in that vector. Okay, so it just looks at the vector, what's the largest absolute value, and returns it. That's a max norm. Okay? So we're not using L2 distance or L1 distance. We're using max norm, which is a very, very fine or coarse notion of distance, depending on how you're thinking about it. So the Bellman backup has a really special property with respect to the max norm. It's called a contraction operator. And what this means, if you take any 2 points, so our points here are value functions, right? Any 2 value functions, and you apply the operator, they get closer together. Okay? So that's what it means to have a contraction property for an operator. You take any 2 points, you apply the operators, and they get closer together. And there's an appendix. There's a proof in the appendix. It's actually it's not a complex proof. You just need algebra more or less to do this, and you write down the definitions. Now, if you have this property, what do you think intuitively? What does it make sense that if you keep applying the operator, it will converge to? Right? You kind of visualize it like all points. Right? If you draw it on the board. All points, here, this is a value function space. All points, if you apply the operator, are kind of getting closer to one another, right? Somehow. I don't know, maybe it didn't work for this one here. Maybe it did, if this was small. But they're somehow all getting closer to one another. And if you applied it to these results, they would get closer to one another. So it feels like they're all kind of converging to one thing, right? And that's sort of what operator theory tells you. If you've got a fixed point and you have this property, they're going to, it has to be the right type of contraction, they're going to converge to a fixed point, right? And there's just one fixed point in this problem, so you're going to converge to the optimal value function. Right? So you just think of it as like this big sphere, and it's just kind of collapsing. The balloon is just collapsing to a fixed point. And so the details of this are, mathematically like this. So this is the distance of the original value functions, right? This is the max norm distance, right? So this would return the maximum absolute difference between any state value. And it's saying if you apply the operator, the distance is going to be less than or equal to beta times this distance. And beta is less than 1, greater than or equal to 0. And so this distance has to be smaller than the original distance, right? And it's sort of multiplicatively smaller, which is really convenient for us. It's not additively smaller. So I think it's probably a good time to stop. We're going to be able to use this property next time to prove that, we've kind of almost proven it, but we'll just go through the details now of how to prove that value iteration converges. And then we'll move on to the other properties of value iteration.
I have